Great pleasure to open the afternoon session of our conference, and let me introduce the chairman of the afternoon session, Professor Seiichi Kamada. Please.
Thank you. It's my pleasure to attending this conference. The first speaker of this session is Professor Madeti Prabhakar at Indian Institute of Technology, Lopar. His talk title is on certain families of waving knots.
Thank you. Thank you, Professor Kamada. First of all, I would like to thank the organizers for giving this opportunity. So title of my talk is on certain families of waving knots. So in fact, my main objective is to talk about unknotting numbers. So even though we are not completely successful in giving the exact unknotting numbers of some waving knots, but in the process, we are able to give some determinant exact formula for the determinant of two families of waving knots. So I'll be presenting those. So for unknotting numbers, we have very limited number of tools to explore the lower bounds and upper bounds. In fact, upper bounds is much easier, but finding the lower bounds is most difficult part. Earlier, many mathematicians like Licorice and Millet explored some polynomial, and through that, in fact, they had given some lower bounds. Signature of a knot is, which we all know, that this using signature also one can give the lower bound for the knotting numbers. Recently, I think in 2004 or 2014, Miyazawa had given some tools which will help in actually evaluating some lower bounds. So here I will start my talk with some preliminaries, and then I will discuss for certain families of waving knots. I'll discuss how we tried finding the unknotting numbers and how we explored giving exact formula for the determinant of certain families of waving knots. So the unknotting number, which is a very important invariant in knot theory, is in fact denoted by U of k, is the minimum number of crossing changes required to transform k into the unknot. So simple examples for trefoil knot, the unknotting number is 1. For 7-3 knot, it is 2, and for 7-1 knot, it is 3. In fact, up to 10 crossings, most of the unknotting numbers are well known. There is another way of defining these unknotting numbers, that is using the Gaussian distance. So for two knots k and k dash, the Gaussian distance from k to k dash, which is denoted by dg of k comma k dash, is nothing but the minimum number of crossing changes required to transform k into k dash, where the minimum is taken over all the diagrams of k, from which one can obtain this diagram of k dash. And for example, if I'm taking the Gaussian distance between trefoil knot and figure 8 knot, this Gaussian distance is 2. In fact, it was showed earlier that if k dash is trivial knot, then the Gaussian distance is nothing but the unknotting number of the knot k. So this is also actually helps us in finding unknotting numbers, but finding the Gaussian distance itself is difficult. Of course, another most difficult part is try to find unknotting numbers for a certain families of knots. One can create nice families by using these braids. In fact, some interesting families can be constructed using the closure of braids. For example, if I'm taking any pair of integers p comma q, one can define a torus link of type p comma q as a closure of a p strand braid. This sigma 1, sigma 2, etc., sigma p minus 1 all for q. So in the morning, I think Tatiana already discussed the braids. So I hope it's very clear to everyone that this particular closure of this braid gives the torus link of type p comma q. And whereas if I'm taking the GCD of p comma q is equal to 1, then obviously I will get a torus knot, one component knot of type p comma q. So here are some simple examples how these torus knots can be constructed using the closure of braids. For 3, 2, 3, 1, and it's a link for 1, and here 8, 19 knot. And obviously this is one of the idea to even think about weaving knots, because weaving knots, the family of weaving knots, are also very close to this torus knots. In fact, one can construct the weaving knots also using the closure of some braids of type P, Q. Why these Taurus knots are important? In fact, other than twist knots, this might be the only class of or family of knots whose unknotting numbers are exactly known, which is P-1 into P-1 by 2, which was provided by Mroka and Kronheimer in 1993 to 95. Between 1990 and 95, they had given this unknotting number. Now, if you look at the closure of this particular braid, which is sigma 1, sigma 2 inverse, sigma 3, sigma 4 inverse, and so on whole power q, which is a P-1 P strand braid, the closure, this particular closure gives the weaving knot of type P, Q. The only difference between the Taurus knots and this is the crossing changes at alternating positions. So obviously, one may think as unknotting number for Taurus knots of type P, Q is already known, one may think that it is also easy to find out the Taurus unknotting numbers of these weaving knots, which is not the case. Okay, for example, see, here are some examples whose closures are mentioned. So now, is there any method at least to find out the lower bounds and the upper bounds? One simple method to find out lower bounds is the signature. But finding the signature using the Seifert matrix and the Seifert cycles, that itself is a complicated one, especially when we are talking about a particular class or family. So one way of doing that is, in fact, by using one of the results stated by Lee. First, to even go to that statement, let me go through some of these preliminaries. A positive crossing is what it is shown here. Essentially, this is the if we are taking the overstrand and by taking the anti-clockwise direction, if you are merging with the understrand, then you can say that that is a positive crossing. And if it is in the clockwise direction, then we say it is a negative crossing. Similarly, there are if you take the checkerboard coloring of a knot diagram, the A regions are the ones which, by taking the overstrand and going through anti-clockwise direction to the understand, and what are the area that is sweeping, those are A regions, and the other way around is B regions in the clockwise direction when we're considering. Now, there are two types of transformations. One is this A smoothing, and the other one is B smoothing. Okay. A smoothing is essentially the one at a crossing if you are merging such that both the A regions are merged, then say it is a smoothing. And when we merge the B regions, we call it as a B smoothing. These are some of the local transformations that are crossing. So if I am considering C of D to be the number of crossings of D and X of D to be the number of negative crossings of the diagram D, and Y of D to be the number of positive crossings of the diagram D, and O of D is the number of components of the diagram obtained by A smoothings at every crossing, then it is possible, especially for the case when the diagram is given to be oriented non-split alternating link L and a reduced alternating diagram D of L, then one can easily find out the signature of that particular link. That is given as the number of components of the diagram obtained by A smoothings at every crossing minus the number of positive crossings minus 1. So finding this way is much easier, and in fact weaving knots falls into this particular category. So if you look at the weaving knots of type 2k plus 1 comma 1, the signature turns out to be 0, which is not of much help. Whereas if you look at the signature for the weaving knots of type 2k comma n, then it gives minus n plus 1. As I mentioned earlier, that signature is one of the lower bound. To be more specific, sigma of k, the signature of k by 2, this acts as a lower bound for the unknotting numbers. So in case if GCD of 2k comma n is equal to 1, then unknotting number of these weaving knots of type 2k comma n is greater than or equal to n minus 1 by 2, just by using this result. Okay, so another simple example that you can see is if I'm taking weaving knots of type 4 comma 5, there are exactly 10 positive crossings, and if I am means the A smoothing at each of these crossings, I will be getting 7 components, and then I can see the signature is nothing but 7 minus 10 minus 1, which is in fact minus 4. Therefore, the unknotting number for the weaving knot of 4 comma 5 is actually greater than or equal to 4 by 2, that is 2. Okay, so in fact, there are other, this is one lower bound. There are other lower bounds possible through Jones polynomial. So how we actually get the lower bounds using the Jones polynomial? In fact, this result is by Licorice and Millet. So let me go through first what is the Jones polynomial. It is a well-known invariant. If I'm taking a trivial knot, then the Jones polynomial at for that k, the trivial knot is 1, and one can use this skin relation to satisfy some skin relations. Using this skin relations, it is possible to actually give Jones polynomial for every knot, where this d plus d minus d naught are the identical link diagrams except at some neighborhood of a crossing, where these are shown here. Okay. So how this will be helpful? In fact, a few questions are still open with respect to this Jones polynomial. Is there any knot whose Jones polynomial is 1, but it is not a trivial knot? For Jones polynomial, especially for torus knots of type P, Q, there is an explicit formula. That formula is given like this: t power p minus 1 to q minus 1 by 2 into 1 minus t power p plus 1 minus t power q plus 1 plus t power p plus q by 1 minus t square. But this type of, even though weaving knots looks very similar to the torus knots, it is still not known the explicit formula for the weaving knots of type P, Q. So finding such an explicit formula itself is also very interesting. In this Jones polynomial, why this Jones polynomial is important in our case? See, if at t equal to e power 2 pi I by n, for n equal to 1, 2, 3, 4, 6, and 10, or in fact, these Jones values are very interesting because of their relationship with some other knot invariants. Okay, so these are mentioned in the Jones paper, this algebras. And out of these, my interest is in checking for n equal to 2 and n equal to 6. For the case when n equal to 2, this turns out to be t equal to minus 1. Therefore, there is a nice relation between vk of minus 1 with the determinant of the knots. And at n equal to 6, it turns out to be e power pi I by 3. And this finding the Jones polynomial at this value will help me to find out some other lower bounds for the unknotting numbers. So my main objective is for this type of weaving knots of type 3, n, and weaving knots of type P, 2, I would like to explore or find the values of the Jones polynomial at t equal to e power I pi by 3 and t equal to minus 1. So at minus 1, this particular result is well known. The determinant of knot can be evaluated, can be obtained by taking the modulus of vk at Jones polynomial at minus 1. Okay, so some of the examples here for half link, it is determinant is 2. For 5, 2 knot, the determinant is 7, and this white haired link, the determinant is 8. Okay. So another, as I mentioned, another important value is at t equal to I pi by 3, and how it is going to help me to find out the lower bounds. So let me assume that L be the link in the three sphere with the mu of L components, and DL be the double cyclic cover of S3 branched over L, and H1 be the first homology group of DL with coefficients in Z3, and NL be the dimension of this vector space H1. Now, Licorice and Millet showed that the Jones polynomial at e power I pi by 3 is nothing but plus or minus I mu the number of components of L minus 1 into I into root 3 whole power NL, where this NL is the dimension of this one. And Miyazawa proved that for any two knots K and K dash, the Gaussian distance between K and K dash is greater than or equal to the difference between these dimensions. And in particular, if my K dash is trivial, then I can see that unknotting number is actually greater than or equal to Nk. Therefore, this dimension acts as a lower bound for the knots, unknotting numbers. So my goal is to evaluate the Jones polynomial at t equal to minus 1 and at t equal to e power I pi by 3 to explore the lower bounds and also to find out the exact value for the determinants of the weaving knots of type 3, n and P, 2. So obviously finding the values at these t equal to e power I pi by 3 and minus 1 is not an easy task unless until we have some formulas or some simple form of writing the Jones polynomial. And Mishra and Stefford studied these weaving knots of type 3 common extensively, and actually they proved several results. For instance, one of them is this, they had given this formula that Jones polynomial for weaving knots of type 3 comma n of t is specifically can be given as t power minus n minus 1 into this form with coefficients also given respectively like this in the recursive forms. Okay, so these, in fact, using these only will be able to evaluate this. In fact, rearranging the same coefficients and the Jones formula in the form of matrices, what I can see is the Cn of t can be written in the form of this matrix, where C1 of t is specifically given this matrix, and for n greater than or equal to 2, what we have is the Cn of t is nothing but capital M of t into Cn minus 1 of t, where capital M of t is given this particular matrix. Okay, and then the Jones polynomial turns out to be in a simple form that is nothing but z of t into t power minus n minus 1 into capital M power n minus 1 of t into C1 of t, where the z of t is given to be this matrix 1 plus t square, 1 plus t into t square into this particular matrix. Now it turns out to be in a simple way, but still the ambiguity is I can take as large n as possible, then how to compute these things. So for that, one simple observation is if I am taking omega is equal to e power I pi by 3, this particular omega satisfies the irreducible polynomial x square minus x plus 1. So I'm rewriting this Cn as Cn of t as Cn of omega, capital M has to be M of omega and z is equal to z of omega. And this particular term t power minus n minus 1 into capital M minus m power n minus 1 of t. This particular term, if I replace with capital En, which is omega power minus n minus 1 into capital M power n minus 1, then the Jones polynomial can be simply written as z an c1. Now, we showed that for omega is equal to e power I pi by 3, then the Jones polynomial at this particular value, that is e power I pi by 3, is nothing but 3 if n equal to 4k, and minus 1 if n equal to 4k minus 2, and 1 for all the other cases. So how we obtain this? One simple observation is what are the matrix that we had taken here. This matrix satisfies a polynomial x power 6 plus omega x square. So from there, one can see that capital M power 6 is nothing but minus omega capital M square. So using that, now if I be able to calculate these ANs, then what I can observe is the A3 plus 4n turns out to be A3, A4 plus 4n turns out to be A4, A5 plus 4n turns out to be A5, and A6 plus 4n turns out to be A6. Now, for any positive integer k, if I am looking at the Jones polynomial for the weaving knot of type 3, 4k, because it is of the form 4k, it is nothing but z a4k c1. This a4k is nothing but a4 because of the relations that we obtained. So from there, now it's a simple matrix, right? So one can easily calculate the product. And as omega already satisfying this irreducible polynomial x square minus x plus 1, using that, by calculating this, the value turns out to be 3. In a similar lines, one can actually calculate the Jones polynomial for the weaving knots of type 3, 4k minus 2. It turns out to be minus 1 for all those k greater than or equal to 2. For the case when k equal to this particular term equal to 2, this weaving knots of type 3, 2, this Jones polynomial turns out to be minus 1. For all other cases, it is as given here. Okay. So now we will be using the Licorice-Millet's theorem and to find out the dimension. So dimension of this first homology group, this turns out to be 2 if my n is equal to 4k and 0 otherwise. So if my GCD of 3, 4k is 1, then obviously this unknotting number will be greater than or equal to this number, okay, this dimension. So this directly we can find out because we already know what is the Jones polynomial at e power I pi by 3. So by using this Licorian-Millet theorem, one can observe this dimension and W turns out to be 2. Okay, so other values are also calculated in similar lines. So specifically for unknotting number, one can say that it is greater than 22. In fact, it is not a great help because the lower bound is always either 2 or 0 for these weaving knots of type 3, n. Nevertheless, we tried exploring the determinant also, and we are able to find exact value for the, in fact, exact formula for nice formula for the this determinant of weaving knots of type 3, n. So in this, to find out the determinant, what we observe is, in fact, if you look at this Cn0, Cn1, Cn2, and Cn21, they are not depending on this Cn2. And if I look at -1, this mod of weaving knot, this Jones polynomial for the weaving knots of type 3, n, this turns out to be simply mod of Cn, 12 of -1 plus Cn, 21 of -1, which is nothing but the determinant of these weaving knots of type 3, n. So for that, we explicitly given the formula, that is determinant of this W of 3, n is nothing but -2 plus 1 plus 5 whole power n plus 1 minus 5 inverse whole power n, where 5 is the golden ratio, 1 plus root 5 by 2. So to formulate this result, as we already observed that these coefficients does not depend on C2 types. So one can obtain this Z tilde from Z of -1 by deleting the third column, and from M tilde can be obtained from M minus 1, M of -1 by deleting the third row and third column, and C1 tilde can be obtained from C1 of -1 by removing the third row. So then what we get is J tilde will be like this, M tilde and C1 tilde. Now what I can observe is this M tilde. The characteristic polynomial of this particular M tilde is x power 4 plus 4 x cube plus 4 x square plus x, and the eigenvalues turns out to be 0, -1, 3 plus root 5 by 2, and -3 minus root 5 by 2. So what I can see is that they have distinct eigenvalues. Therefore, this matrix M tilde is diagonalizable, and using that, one can check that M tilde can be written in the form of P, D, P inverse, where P, D, and P inverse are as shown here. Now, once we have a nice formula for M tilde, then finding this determinant for the weaving knots of 3, n turns out to be simple, because it is nothing but Z tilde at -1 and -1 power -n-1 into capital M tilde power n-1 into C1 tilde. So by evaluating these, one can see that this is nothing but -2 plus 3 plus root 5 by 2 whole power n plus 3 minus root 5 by 2 whole power n. So this, if we want to consider the golden ratio and want to convert in that form, then it turns out to be exactly this form. It is not the first time that this formula is given. In fact, earlier OSPER in 2005 had given this determinant of weaving knots of type 3, m using Fibonacci numbers. And in fact, Kim, Stees, and Palmer, they in fact define this spiral knot as S of k, n, epsilon, where it is exactly looks like similar to the P minus n-1 braid here, where the epsilon 1, epsilon 2, and epsilon n-1 can be either plus or -1. So it is neither comes under the weaving knot class or Taurus knots, but specifically if I'm taking this 1 and -1 alternatively for epsilon i's, then and this n equal to 3, then this spiral knot turns out to be weaving knot of type 3, k. Now they had given the determinant of this particular spiral knot is L2k -2, where L2k is the Lucas number. Lucas number is also very similar to Fibonacci number, where Lk is in fact Lk -1 plus Lk -2. Only the initial values are different. That is L1 is equal to 1, and but L0 is equal to 2. So because of that, it differs a little bit from the Fibonacci number. So here is this way also one can get exact the determinant of the weaving knots of type 3, n. So these are some results based on the results for n lying between 2 and 17. The determinants can be easily obtained by using the formula given. And if you look at the Jones polynomial at e power I pi by 3, they turn out to be repetitive in the sense -1, 1, 3, 1, and the repeat. Okay, so using that, what are the upper means unknotting numbers, one can see the based on the lower bounds and upper bounds. Upper bounds can be easily find out by using the different methods. I will give few strategies in this talk. So by using that also, you can actually specifically mention for 8, 18, it is exactly equal to 2. For 10, 1, 2, 3, it is 2. And for some of them, it is the lower bound we can mention is 2. Another important class that we would like to explore is Jones polynomial for weaving knots of type p, 2. So the way for 3, n, we have a nice formula, but here a closed form formula for Jones polynomial for weaving knots of type p, 2 is not known. But however, it is possible to give some recursive formula, and finding the recursive formula is very easy. Just by using the skin relation diagram, one can easily find out the Jones polynomial in the recursive formula. So if you observe that this Jones polynomial for the units of type p, 2, especially for p equal to 2, it is minus of t power 5 by 2 plus t power 1 by 2. And v notes of type 3, 2, it is minus t power minus 2 minus t inverse to z into Jones polynomial for the v notes of type 2, 2. So one can write in the recursive formula. Once this is that, then for every integer n greater than equal to 2, one can give Jones polynomial for the v notes of type 2n, 2, which is t square into this plus tz into the Jones polynomial for this v naught. Similarly, for Jones polynomial for v notes of type 2n plus 1, 2 is given in this way. So how we are finding this? It is a very simple formula by using the skin tree diagram. So by making the applying the skin relations here, one can check that this weaving knot of type 2n plus 2 can be written in the form of these two weaving knots, and hence we can have this nice recurrence relation. Now, using this recurrence relation, it is much easier to find out at t equal to e power I pi by 3. We use the same technique, but here the values will differ a little bit in the sense that the Jones polynomial for the weaving knots will not help much in finding the lower bounds here. So if you look at carefully, this if I'm rewriting the Jones polynomial at weaving knots of type 2n, 2 at e power I pi by 3 as v2n and v2n plus 1 for this particular Jones polynomial, then this can be written in the form of v2n is equal to this, and v2n plus 1 is equal to -1 if n is common to 1 or 2 mod 4, and 1 in the case if n is common to 0 or 3 mod 4. The idea is similar. You substitute the omega is equal to e power I pi by 3 in the recursive formula that we obtained. Okay, and then z is equal to I, and for n greater than equal to 3, what I can see is this v2n plus 1 turns out to be minus v2n minus 3, substituting the values based on the recursive relation. And then for n greater than equal to 3, what I can observe is v2n is nothing but minus v2n minus 4. And for initial values, v2 is -1, v3 is v3, v5 are both -1, and v4 is equal to √3. So substituting all these values, it is easy to find out the Jones polynomial exactly at this omega is equal to e power I pi by 3. But finding the dimension is not of much help, because dimension gives only the value 1 if my p is equal to 4k and 0 otherwise. So in this particular case, even though we explored or tried to find out the lower bound, it is not of much help, because the lower bound is either 1 or 0, which is not much help to find out the unknotting numbers. But finding the determinant of this particular class turns out to be interesting, because it exactly gives a very nice formula. The method is a little bit different than what we explored before. So by substituting t is equal to -1 in the recursive formula of this particular Jones polynomial for the weaving knot of type p, 2, by taking an equal to all the Jones polynomial at 2n, 2 and Bn is equal to Jones polynomial for the weaving knots of type 2n plus 1 comma 2. What I can observe is Z is equal to 2i, and A1 is equal to minus 2i, A2 is equal to minus 12i, B1 is equal to 5, and B2 is equal to 29. So in fact, these are the initial values, and then later on you can see some recursive relation. So based on these recursive relations, by solving them, we get two linear recurrence relations. And one can observe that the characteristic equation of both these linear recurrence relation is in fact x square minus 6x plus 1 is equal to 0. And they have two distinct roots, 3 plus 2 root 2 and 3 minus 2 root 2. Therefore, the solution will be of the form C1 into this C3 plus 2 root 2 whole power n plus C2 into 3 minus 2 root 2 whole power n. Now, by using the initial values of these A1, A2, and B1, B2s, we can evaluate and find out the exact values of C1 and C2. So that turns out to be An is equal to this minus I by 2 root 2 into this, and Bn is equal to 1 by 4 into this value. And the determinant of this V naught is nothing but mod An, because the way we had taken Ans and Bns. So the determinants actually gives up this An and Bn gives you the determinants of the knots, the mod of these values. So that is how we can easily show this exact formula for these determinants. Now coming to the unknotting numbers, let me first see for these values 2 less than equal to p less than equal to 17 for this particular weaving knots of type p comma 2. It is no help to look at the lower bounds, but for the determinant we can have based on the exact form we can find out all the values. Whereas if you look at the Jones polynomial at e power I by 3, they are not exactly repetitive, but it is minus times of the repetitive values. That is minus I, minus 1, root 3, minus 1, and minus of these values. That is I, 1, minus root 1, root 3, and 1, and again minus of these values. It repeats like that. So that is one observation we can have from this. Here we tried exploring unknotting numbers for the weaving knots of type 2n plus 1 comma 2. So if you look at this 2n plus 1 comma 2, by making a crossing change here, this actually converts into, in fact, you can have a nice unknotting sequence. The first example that he mentioned here is 8, 12. By making a crossing change here, it turns out to be 4, 1, and then it turns out to be trivial. In general, if I'm taking any weaving knot of type 2n plus 1 comma 2, by making crossing changes like this, the means negative crossings in the first strand, then you can observe that exactly by making n crossing changes, this will turn out to be trivial. And in fact, another important thing that can be observed here is in the whole unknotting sequence, all the knots that are coming in between, they are also weaving knots of type 2n minus 1 comma 2 and 2n minus 3 comma 2, etc. so on. So obviously the unknotting number for this particular class is less than or equal to n. But what is the importance of this? If you're looking at with respect to crossing numbers, then it is actually the upper bound is 2n. But here the upper bound is coming out to be n. Here I would like to deviate a little bit, because in this case finding the lower bounds is not an easy task. But if I'm taking a virtuality here, this particular weaving knot of type 2n plus 1 comma 2, where my first crossing is a virtual crossing, then it is possible to give some lower bounds. So there is a nice lower bound for the virtual knots, that is the odd width, which is the sum of the signs of all the odd crossings of the knot. So for this particular class, if I'm looking at that odd width, then that also turns out to be n. Therefore, if this is a virtual crossing and the weaving knot is it is of the type weaving knot of type 2n plus 1 comma 2 with the first crossing as a virtual crossing, then the unknotting number turns out to be exactly equal to n. Okay, but for classical, as there is odd width turns out to be 0, that is not of much help. But obviously with that we may conjecture that the unknotting number of these weaving knots of type 2n plus 1 comma 2 is exactly equal to n, which we are still not aware how to evaluate that. So if I'm looking at the unknotting or unlinking numbers of some of these weaving knots, one can see that for 2 comma q weaving knot, it is nothing but T of Taurus knot of type 2 comma q. Therefore, the unknotting number is q minus 1 by 2. For others, for 3 comma 2 and 3 comma 3, in fact, all these whatever that we are able to see based on the lower bounds or some based on the availability of the unknotting numbers. These unknotting numbers are known. For 7 comma 2, it is either 2 or 3, which is of the form this 2n plus 1 comma 2, and 5 comma 3 it is 2. Okay, so some unknotting strategy one can think is based on unknotting crossing information for Taurus knots. For example, if I'm taking a Taurus knot of type 4 comma 4n plus 1, or to be more specific, Taurus knots of type p comma pn plus 1, when my p is even, we already in one of our earlier papers, we are able to give unknotting crossing data, minimal unknotting crossing data for the Taurus knots. So there, if you are making this crossing information, if you make the crossing changes at this crossing information, then it turns out to be trivial. So if you look at, there are exactly 6 crossing changes that you need to make for a Taurus knot of type 4 comma 4n plus 1 to make it into trivial. But the same strategy, if you would like to explore for weaving knots, here also, if you make exactly 6 crossing changes, then it is possible for you to convert this particular weaving knot into trivial. But in the case of when p is odd, the case is a bit different. So if I'm looking at this particular case where when my p is equal to 7, by making these crossing changes at 21n crossing changes where my Taurus knot is 7 comma 7n plus 1, then it turns out to be a trivial. Now, adopting a similar type of here means strategy here for weaving knots of type 7 comma 7n plus 1, the difference is, see, wherever that over crossings are there, so under crossings in the weaving knots that can be converted to over crossings, and where these crossings in the Taurus knot where we need to make these crossing changes, if they are already over crossings here, we are not going to touch anything. If they are under crossings here in the weaving knot of type 7 comma 7 plus 1, we are not going to touch those. And looking at that, in this particular case where my p is odd, we will have less number of crossing changes required. So if I'm looking at weaving knots of type 7 comma 7n plus 1, then the number of crossing changes that I need to convert this weaving knot to a trivial one is 18n crossing changes. So this particular strategy for all the Taurus knots of type p comma q we explored in one of our earlier paper. But the same strategy when we are trying for general case, it turns out to be a bit difficult. But for the case of this particular p comma pn plus 1, it turns out to be a bit easy. Bit means essentially we can see a bit less number of crossing changes required to convert, but still it is far away from finding the unknotting number. So there are many questions one can pose out of this work. In fact, if I'm looking at for this particular case, this bounds for unknotting numbers for the weaving knots of type p comma and p plus 1. For the case when p greater than equal to 2 and n greater than equal to 1, what I can observe is if my p is even, it is possible to find the lower bounds using the signature, the way we mentioned in the beginning, which is based on the result of Lee. And for upper bounds, the strategy that we approached based on that, if my p is even, it turns out to be np into p minus 1 by 2. And if my p is odd, then it turns out to be n into p minus 1 whole square by 2. So whether am I going to get exactly equal? Obviously no. For odd case, the lower bound turns out to be 0 in this particular case. The signature turns out to be 0, so it is not of much help for the case of odd. For the case of even, we have this result. Now, out of these, we have many questions. First, is it possible to find an integer n such that unknotting number for the VV knots of type 2n plus 1 comma 2 is less than n? Because I mentioned by changing a little strategy and giving the first crossing to be a virtual crossing, then it turns out to be exactly equal to n. So can we say that this unknotting number for this particular class is exactly equal to n? So so in another way, if you be able to find an integer n such that is it possible to say the unknotting number is exactly less than n? And the problem is even though we have some lower bounds for the unknotting numbers for the weaving knots of type 3 comma n, especially for the case when it is a knot, then finding this unknotting number will be very interesting. So in other problems, one is finding the unknotting number for the weaving knots of type p comma and p plus 1, where for a particular case when p is even, we have both lower bounds and upper bounds. But for other cases, we are still not aware. And obviously, only for the case for 3 comma n and p comma 2, we are able to give explicit formula for the determinant of the weaving knots of those weaving knots. But is it possible to give explicit formula for different types of weaving knots? And other than these, we are considering a class which is very similar to Taurus knots. Just the changes are in the crossing changes. When we are looking at the closure of a toric braid or closure of a braid. So there are many other instead of because if you look at Taurus knots, there are p minus 1 alternating, whereas in weaving knots, if you look at it, is completely alternating diagram. So instead of completely alternating diagram, we can in fact create different type of classes by considering m alternating knots from the closure of the braids. Okay. So from there also one can ask many questions and try to find out unknotting numbers. So there are different problems just by taking the closures of these weaving knots or knots which are their projection is very similar to the Taurus knots. One can try to find out these unknotting numbers by using some of the strategies that we specified. So these are some of the references. In fact, this is the paper where they mentioned about the dimension of Jones polynomial e power I pi by 3. And Miyazawa in his paper, he mentioned about the Gaussian distance and the relation between the dimension and the unknotting number. And these are some of the references. So this is the theory used by Kronhammer and Broca, that is Gauss theory, to establish the exact unknotting numbers for the Taurus knots of type p comma q. Okay. So I will stop here. Thank you.
Thank you. Do you have any questions or comment? If you have a question, please turn off your mute and ask your question. Hi, Rama.
Oh, hi.
Do you have
So,
a question?
yeah. So about weaving knots of type this 3 comma whatever that n.
Yeah.
So then it's actually a knot. So you said the explicit formula for Jones polynomial is not known. So I just have to add that now we have an explicit formula, which I'm going to anyway, I'll be putting on archive. And maybe that formula, because the directly the coefficients are in terms of binomial coefficients and Pockheimer's symbols. So maybe that can help. Do you think that if explicit formula was known, the unknotting number computation could have been easier?
No, ma'am. Just because here in this case, it is so happening that evaluating e power I pi by 3 turns out to be easy. So irrespective of what of the formula that is given by you in your paper and Stefan paper, it's using that itself we are able to evaluate. So explicit formula may be helpful in some other way, but may not be for the unknotting number.
I see.
But
So
for
right
other,
now, that is for unknotting number is you just have some bounds for upper bound and lower
yes,
bound.
and lower bounds.
And
Yes.
that's all. That also for just 3, n and p,
Yes,
2.
3, p, 2. We tried evaluating the same way, but unfortunately, the value turns out to be either 1 or 0. So it is not of much help, even though we explored that just for our own understanding. But we observed that that lower bound is of no help because it turns out to be 1 most of the cases and 0 in other cases.
So the bound that you got for 3, n, can that be generalized to any odd, like WPQ when P is odd?
Yeah, of course, if we have an explicit formula for the VV knots of P, Q, exploring that will be interesting. This finding the
So
Jones
explicit
polynomial using that
formula for
explicit
what?
formula.
You mean
Jones
explicit
polynomial of type.
formula. So that anyway, we have put it on archive, not the recursion we have for
Not for
PQ.
3, n, not for 3,